Okay, so welcome to the third and final installment of the Coxeter lectures to be delivered by Ilyashenko. He will keep telling us about the finiteness theorems for limit cycles. Go ahead.
Thank you, Gal. So the lecture today will be a little bit different from the previous ones. The previous two lectures had a mostly survey character. Today I will have some proofs, yet in a very moderate quantity. The plan of the lecture is to define the super exact asymptotic series. This series will be the major subject of the lecture. There is one parameter which is important for this series. It is called index, and its definition is rather lengthy. And the statements to be proved is the lower estimate theorem. So in the previous lecture, I partly defined cochains of class FC1. The definition contains two parts. The first part is the regularity part. This is the description of the cochain, which is the cochains of class FC1 are specific cochains with their specific partition and specific co-boundary estimates. So this description was very briefly shown in the previous lecture. It is analogous to the description of simple cochains FC0 that was presented in more detail. But the second part of the definition is cochains of class FC1 are sectorial cochains, regular sectorial cochains, that admit asymptotic expansions. And these asymptotic expansions are very far-going generalizations of Taylor and even Dulac series. And these series were not yet defined, so the class FC1 is not yet defined. But when it will be defined, then the following theorem will be meaningful. Any cochain of this class, which is not zero, not only does not oscillate, but on the real positive ray, it admits a lower estimate by some decreasing exponential. So this is the statement that we will discuss today. And it is extremely important for the proof of the finiteness theorem because the monodromy map of a polycycle is expressed through, or the alternate polycycle is expressed through simple and sectorial cochains. And the estimates like this for these cochains are crucial for the study of the monodromy map of this polycycle. So this is the plan. And now I will discuss an example, a very simple example of a composition that occur when we study the monodromy maps of polycycles. This is a composition of exponential, then almost identity map, identity plus phi, and in our example, phi is a decreasing exponent. It is exp negative psi on the real axis and exp negative zeta in the right half plane. And then goes logarithm. So we take a conjugacy by exponential of this map identity plus phi. The result will be the following. The resulting map will be identity plus double exponential, not a single one. like phi was. And this is a crucial property of the maps that we study. So here on the screen, I show a very elementary calculation for this map. And the two lower lines give two expressions. The map is zeta plus a convergent series whose terms are doubly exponentially decreasing. Now, there are two representations of this series. For the first representation, there are numeric coefficients and exponentials with exponents like this: negative kx zeta minus k zeta. The second representation is the exponentials have exponents only negative kx zeta, and the coefficients are functional coefficients, but incomparable with the double exponents. So the situation is a little bit similar to the Yulij series, where we have exponential terms multiplied by polynomials, and these polynomials may be polynomials of zeta, may be considered as coefficients of this series. So the question below is, where is the exponent and where is the coefficient? And this question shows that in the series that we will encounter, coefficients and exponentials are in a sense mixed. And this will be a serious problem in the study of this series. So I give a brief sketch of the definition of super exact asymptotic series of class 1. The notation is has the following nature, the following origin. In Russian, the name of the series is сверхточные асимптотические ряды. STAR are the first letters. And I took this Russian abbreviation for the English use because star sounds good. So series of the class 1, star 1, they have the form, very usual form. Every term is a coefficient times exponent, exponential of exponent. The coefficient is aj, and ej is exponent. Every series has an index to be defined. This index is a finite subset of the 0-1 interval. And this index is not uniquely defined. And it depends on the representation, on the particular formula with which the terms of the series are expressed. So the set of exponents is denoted by E1. The set of coefficients is K1. The coefficients have non-negative rank. The set of all the coefficients of rank R is denoted by K1R. The rank will be used to define the set of the coefficients inductively. The set K1R is defined by induction in R as described below. So first, what about the exponents? The exponents are just partial sums of the Yulij series with some restrictions. The coefficients are real polynomials. The exponents are mu j's positive or negative numbers. And the sum is, no, not negative, non-negative numbers. Mu j's are non-negative numbers. And they cannot, mu j's cannot exceed 1. Moreover, if mu j equals 1, then the polynomial before this exponential is constant. So the leading term of the exponent is constant time exp zeta. Probably this constant is 0. In any case, the limit, the exponent divided by x psi on the real positive axis at infinity exists. It is called mu of the exponent, and in words, it is principal exponent of the term. So in this way, I described the set of exponents. Now, the set of coefficients. As I said, they are defined by induction in R. We start with R equals 0, and the set K1, 0 is defined in a very simple way. This is the set of all the cochains of the class FC0 that were defined in the previous lecture. What I should recall about them, that they have no more than exponential growth, are approximated by the Yulij, by the asymptotic Yulij series, and therefore and satisfy the Fragment-Mendeleev theorem. That is, if the cochain has a 0 Yulij asymptotic series, then it is 0 itself. So this is what we remind about FC0. And this is a very specific set of coefficients. We are accustomed to coefficients that have sort of a finite nature. For instance, for the Taylor series, these are numbers. For the Yulij series, these are polynomials, but in any case, they are given by a finite number of numeric parameters. And in this case, even for the simplest subset of coefficients, the coefficients have an infinite nature. This is an entire cochain of the class FC0, and we do not try to describe it by numbers. So I go on. The set of series of class 1, 0, it is denoted by equiligraphic 1, 0, is the set of the series written in the bottom. The exponents are from E1, the coefficients are from K1. Now we want to describe cochains of the class 1, 0. These cochains will be decomposed in the series that are in the asymptotic series that are already defined. Now we should define the domains for these cochains and what decomposability means. So first of all, the class of domains where the cochains are defined is similar to quadratic standard domains, but different. These are the images of the right half plane with a disk, with some disk deleted, under a map which is identity plus c zeta divided by log zeta. So if you look carefully, they are in a sense narrower than the quadratic domain. The set of such domains is denoted by omega 1. And exactly these domains will be used to say what does it mean that the series is asymptotic for a cochain. The notion is plus decomposability. That is, the series approximates the cochain composed with exponential only in the half plane, or better to say, in a half plane extended a little bit down. So a sectorial cochain is plus decomposable in a star 1,0 sigma, provided that there exists a standard domain of +1 and a positive epsilon, such that for any positive number nu, there exists a partial sum sigma n of the star sigma that approximates the composition f of x with the accuracy of double exponential x power negative nu x psi. So the difference below is estimated by the double exponential. If f is defined in omega, then the composition f of x is defined in log omega. And as we deal with the upper half plane only, we consider the intersection of this log omega with the epsilon neighborhood of the upper half plane. So this is the definition of plus decomposability. And now cochains of plus FC10 are sectorial cochains for which their composition with exponential is plus decomposable in star 10 already defined. So at this spot, we ended up with the definition of a particular set of cochains FC10, the simplest ones. But still, our main goal is lower estimate theorem for cochains, and the scheme to obtain this theorem is just the same as for the cochains of the class FC0. We take an asymptotic series for the cochain, we approximate the cochain by a partial sum with a very high accuracy, and we justify that the partial sum not only does not oscillate, but exceeds some function which majorizes the remainder term. And therefore, the cochain itself does not oscillate. So for FC0 and Yulij series, this was a simple argument going back to Yulij. But now we have a quite different kind of series. We have series whose coefficients have sort of infinite nature. So the particular case of the lower estimate theorem claims cochains of class FC10 admit the following Flower estimate. The cochain itself is greater than some decreasing exponent on the real axis. Here we have exponent of negative 6 psi, and below we use a so-called universal constant C. So when some estimate holds for some constant, we always denote this constant by C. In different estimates, this constant may really be different, but the notation is the same. It does not bring to confusion. So I would like to give a sketch of the proof of this theorem. First of all, let us take a cochain of our class, and let us take the asymptotic series for this cochain. This means that this asymptotic series approximates the composition of the cochain with exponential. We may assume that the exponents have no affine term, no terms alpha, zeta plus beta, or else these terms might be absorbed to coefficients. Instead of the coefficient aj, we take a coefficient bj, which is aj multiplied by the exponential of this linear function. Aj are from the class FC0, and bj, if you recall the definition of the class FC0, is also from the same class. So the smaller terms of the exponents are now of order z squared. Let us take a partial sum sigma n of the series that approximates f composed with exponential, sure, with the accuracy r, which decreases rapidly enough. Now, a very simple trick is applied, which will be applied many times, not in this lecture, but in the proofs of the statements that I do not present here. I do not present the proofs, I will present the statements. Let h be the maximal exponent of the sum sigma n. Note that the exponents are sums of so-called quasi-polynomials, products of polynomials to exponentials, and the polynomials are real, the quasi-polynomials are real, and they are ordered at infinity. One is greater than another if the difference tends to plus infinity. Let h be the maximal exponent of sigma n. For any other exponent, the difference between this other exponent and h tends to negative infinity and tends faster than psi because the lowest term is of order zeta squared. So we express the partial sum as exponential of h times the coefficient a before in the corresponding term where the exponential of h is present, plus the remainder term. And the remainder term is expressed as in the lower line, and all the exponents tend in this sum for R1 tend to negative infinity faster than psi. And therefore, R1 is smaller than A. And H is an exponent from E1. and it is greater than h is greater than some exponent of minus c z. So if we take the principal exponent mu for h, then h is greater than exponential of mu minus epsilon. So x of h is greater than this exponential, and epsilon dominates a and r1, which are in the previous presentation for sigma n. And this is the end of the proof of the lower estimate theorem. It shows how the coefficients that are functions may be controlled in our situation. So it was just the definition of the series of class 1 was interrupted by this theorem, because this theorem allowed us to see how all the machinery works. Now we come back to the definition, and I should say that at the very end of the lecture, there will be another more general version of the lower estimate theorem for the cochains of class FC1. But the scheme of the proof will be the same. So what is the plan of definition of FC1R? This definition is given by induction of R, base of induction, and step from 0 to 1 are already done. Let us now describe the step from R to R plus 1. So we can not think strongly about step from 0 to 1. It will be explained as a particular case for arbitrary R. The induction assumption is that we already know the set K1R. In the base of induction, we know K10. K1R are coefficients of class 1 and rank R. After that, we define the set of super exact asymptotic series of class 1, 0. And this is just the class of series of the form written in the display. So we already have the set of the series. After that, we define the set, C is missing there, with the set FC1R. Given FC1R, we can define the set of coefficients 1R plus 1. And this completes the induction step. We have the coefficients of the next class. We passed from R to R plus 1. To R plus 1. So this is the plan. Let's go. Plus decomposability of sectorial cochains of class 1R, R is defined in the very same way as plus decomposability for a star. I see here a typo. Here I should put star 1R. And this is the only difference with the previous definition of decomposability to the star 1, 0. In that definition, sigma was the star of class 1, 0, and now it is the star of class 1R. All the rest in the definition of decomposability remains the same. But having the set of series and having the notion of decomposability, we define the set of cochains FC1R and just the sectorial cochains that are class decomposable into asymptotic series of class 1R. And now we define the set of the coefficients K1R plus 1. This is the previous set K1R plus the set of the following compositions. We have cochains from the class FC1R just defined and compose it with exponential and with multiplication. When I write circle mu, I mean the composition with the linear map multiplication by mu. Mu is taken from the interval 0, 1, from the open interval. Thus, by induction in R, we defined the series and cochains of classes E1R, FC1R, respectively, for all R in non-negative integers. So we take just the unions, and these unions give us star 1 and cochains of class 1. But in fact, we need another property, another feature of these cochains called index. The definitions are not yet complete because the index notion puts some extra restrictions on the series of class 1. So now we pass to coefficients, to the notion of index, of the index. First of all, a non-formal idea of the definition. A typical coefficient A of star 1 is a composition of a cochain, exponential, and mu. The index of a partial sum takes care of all the mu's that occur in the coefficients of this sum. So, for instance, if we meet a coefficient like written here, then mu will enter the index. But some mu's are in a sense hidden in the cochain F. So this is an idea of how the index will be defined. And now I come to a rigorous definition. The definition is given by induction in R, and the base of induction is for R equals 0. If F is of class FC1, 0, then index F is empty by definition. Now let us take the induction step in the definition of the index. First of all, take a series. Suppose that we already know how to define the index of the coefficients of the series. This will be done below. The index of a series is just the union of the indexes of its coefficients. And here is a new requirement upon the star 1. Despite the index is the union of an infinite set of an infinite number of sets, this union is required to be a finite set. So despite the number of terms is infinite, the index should be finite. Now let us let us define the index of a cochain. We take an asymptotic series for f composed with x, and we define index of f to be equal to the index of the series. An important remark says that asymptotic series for f circle x is not uniquely defined. So we consider the series together with its representation, together with the way it is written. And in fact, we define the index of a pair, cochain and series, but we write index of f for simplicity. And when we deal with the index, we always have the distinguished exponential series that approximates f and take the index of this series. Now we made the following way. Suppose that we know the index of the coefficients, then we know the index of the series, then we know the index of the cochain. And once again, the definition goes by induction in R. So let us take a coefficient from the set K1 R plus 1. U in comparison with K1R. This coefficient has this form, and the cochain is of class 1R. So we know its index. Here is a typo, not 9, 1, but 0, 1 for sure. 0, 1. And the index of this coefficient of this composition is defined as follows. This is index of f. Once again, the coefficient is in the set number r plus 1, and f is in the set number r. Everything is already defined for the sets number r, and we give the definition for the sets number r plus 1. So the index of A is index of f multiplied by mu, this mu, plus the number mu itself. So in this way, the definition of the index is given. It is once again inductive, and it is now complete. Now I switch to the proof of the lower estimate theorem for cochains of class 1. And for this sake, I formulate the principal representation theorem for partial sums of star 1. This principal representation theorem replaces the idea of distinguishing the leading, the major term in the partial sum of a series. It is easy to distinguish a major term in the partial sum of a Taylor series. But in our case, it is in a sense impossible, and instead of that, we formulate the decomposition theorem. The statement is long, it will take several displays, so this is only the beginning. Suppose that we consider a non-zero, non-contractible. This means that it cannot be replaced by an equal sum with a smaller number of terms. Non-contractible partial sum of star 1 with the index written below. Then sigma n, this sum, admits the following representation. You see, I will not read it. It is long and clearly seen. But I will say what is written in the next slide. H1 is an exponent from E1. So no restriction to the choice of H1. H2 is from E1, from the exponents of class 1, but composed with multiplication by mu1. And so on. H3 corresponds to multiplication to mu3, and Hi plus 1 corresponds to multiplication to mu I. A is from FC0, and R is a remainder term that decreases faster than any exponential. That is, it decreases faster than any element of A, non-zero element of A may decrease. So more about the exponents H. Here is what I have said. Now, either HK is 0 or HK grows faster than exponential composed with mu k. For instance, an example of HK from here is exponential of mu k minus 1 multiplied by z. But mu k's do decrease, so mu k is smaller. And therefore, this exponential grows faster than exponential of mu k multiplied by z. And this is this requirement is generalized in the formula here. What about the last exponent? It grows faster than psi, and this is all about the exponents. What about the remainder terms? They decrease faster than the exponentials of the exponents with the same number may decrease. So these are the formulas for the remainder terms, and we will use them later. So I will not give any idea of how the representation theorem should be proved. It is a sort of a technical proof. But if you believe the representation theorem, then you can prove the lower estimate theorem. The lower estimate theorem is repeated. Once again, there is a typo. These are cochains of class FC1, not FC10. And they admit the lower estimate that that is written here by some decreasing exponential on the positive real axis. And this is the repetition of the statement that was already given. So I begin the proof, and this will be the last, next to the last part of the lecture. The last part will be a survey. So let us take a partial sum that approximates the composition F circle X. Suppose that the index is, as written here, mu k's monotonically decrease. I write down the representation from the previous theorem, and I will prove that the sum sigma n decreases as the theorem claims. To do that, I will consider intermediate sums, sk minus 1. So we take just a part of the representation formula. I do not see my, I see on the screen some bar that accompanies zoom. Do you see that my mouse slides over the formula or not?
Yeah, now I see it, yes.
Well, in any case, the sum sk minus 1 is the intermediate part of this expression that begins with xhk and ends with rk. So our original sum is S0, and the most interior part is Si, the exponential of hi plus 1 multiplied by a plus ri plus 1. And the theorem will be proved by the inverse induction in K. So base of induction will be for K equal I. And the statement is that this partial sum exceeds this exponential. So the same mu has the same number as the sum itself. Base of induction is K equal to I. We should prove this statement. Note that hi plus 1 is from E1 circle mu1. Hence, it is greater than negative C exponential of mu1, mu I psi. So amidst the exponentials, sorry, I should, yeah, let me see. Yes, amidst the exponentials with the factor mu k, this term exponential of mu I psi increases most slowly. All the other mu k's are greater than mu I, and this term increases faster. And when I take exponential of this term, it will decrease faster. So now we have a plus 1 greater than this negative c times exponential. And therefore, the modulus of this exponential is greater than this double exponential. So exponential of hi plus 1 is greater than this double exponential. And a plus ri plus 1 cannot spoil this estimate, because a is greater than some simple exponential, simple decreasing exponential, and the remainder term is small in comparison with A. So this completes the induction base. Now I produce the induction step. The induction assumption is that the intermediate sum is greater than the corresponding double exponential for the number k, and we want to prove the same for the previous sum. The previous sum is expressed through the given sum in this way. Here is exponential of hk, given sum, and the remainder term. The remainder term is small in comparison with the sum sk, and hk is in this set of exponents. Therefore, hk is greater than some exponent like this. Therefore, xhk is greater than this double exponent, and by this estimate, the expression in brackets cannot destroy this property of xhk. And this proves the statement that this proves the lower estimate theorem. We apply this to S0 and get the formula that we wanted. So the partial sum decreases no faster than exponential negative c exponential psi, and therefore the cochain itself, for which the partial sum approximates f of exponential, the cochain itself decreases no faster than some simple exponential. This is the theorem that we wanted to prove. And here I stop the detailed presentation for the cochains of class 1. I tried to give you an idea of the techniques that allows us to estimate from below the cochains. Once again, I come to the general setting. The cochains are approximated by specific theories, and moreover, they are subject to the Fragment-Lindelöf theorem. And when we study the cochain, if the series is 0, then by the Fragment-Lindelöf theorem, the cochain itself is 0. And if the series is non-zero, then it does not oscillate, as the study that I presented shows. So this is the conclusion for the lecture today and the previous lecture. And now I want to give a very brief survey of what is going for n greater than 1. So when we consider not alternate polycycles, but polycycles of arbitrary depth, then the cochains involved become more and more complicated. Both their regularity and expandability properties require more details. The partitions that correspond to the cochains that occur on the level n is defined with the use of all the information obtained for the composition on the depth n-1. So the partitions are defined inductively in N. Super exact asymptotic series are defined analogously to what I delivered and also become more complicated. These parallel theories are built up. The only thing is that I found that my previous version of super exact asymptotic theories did not work. And what I presented now is a new version of the theory of super asymptotic series. And for series of arbitrary depth, the parallel theory is developed, but not yet completed. I very strongly hope that I will complete it not in a very distant future. And in my mind, I think about the following possibility, that I will complete all the details, write the final text that will be more readable than the book that I published 30 years ago, and that finally I will deliver the complete proof with all its details to the heroic audience that would agree to attend a 30 hours course, say a course given in 10 days, 3 lectures per day. So these are only dreams. I have no right to stress anything on the subject, but this is the state of matters as of now. And here I end. Thank you.
Okay, so thank you very much. Let's thank the speaker one final time.